Well, thanks for the invitation and thanks for being here after sunset. I would like to apologize for the lack of hard analysis of what follows. It's going to be a very elementary, but I think it's
soft analysis.
Yeah, well, yeah, it's very soft. But I think it's a fun question that I could share here. So I'm going to talk a little bit about displacement convexity for those of you who may not know what it is, and then a tiny bit about point processes, and I will describe an application of this. So let me start with displacement convexity. So displacement convexity is a sub notion of optimal transport. So what's the setup here? I take two probability measures on Rn, and let's say they are absolutely continuous with respect to the bag and compact support, just to make life easy. It's certainly not necessary. So we say that a map T is a transport from mu0 to mu1 when the push forward of mu0 by T is equal to mu1. And in other words, if this equality holds for sufficiently many test functions, so for all f, let's say C0 compactly support in Rn. Okay, and so I'm pretty sure that most of you know this. So then what's the optimal transportation problem is to find T that minimizes among all transports. Okay. So this is the optimal transportation problem with quadratic cost, which is the only thing I will care about today. And as we've learned in one of the first talks of the year, there's this theorem by Monnier that says, well, there exists an optimal transport. T plus, there is some structure about T. T can be written as the gradient of some convex function. Oops. Okay. So that's optimal transportation in 1 minute. And once you have the notion of an optimal transport, actually once you have the notion of a transport, you can define a new notion of interpolation called displacement interpolation. And the basic question it answers is, what's in the middle of mu0 and mu1? Well, you can say, I know an answer for that. Take mu0 plus mu1, divide by 2. That's what we are tempted to say, right? And more generally, you could define nu t as well the usual interpolation between two probability measures. Mu t is a probability measure on Rn, and mu0 is mu0, and mu1 is mu1. Okay. But there's another way to interpolate. So that I will call the usual interpolation. If mu1 is obtained from mu0 by transport T, you could look at Tt, which is this map from Rn to Rn, and then define mu bar t as the push forward of mu 0 by tt. And of course, t0 is just the identity, so mu bar 0 is mu 0, and t1 is just t, so mu bar 1 is equal to so that's a valid interpolation between mu 0 and mu 1. If that's confusing, there is an example that I think clarifies the situation. It's when mu 0, so example, if mu 0 is the Dirac mass at 0 and mu 1 is the Dirac mass at 1, then the usual midpoint is this mixture of two Dirac masses, and the displacement midpoint is just the Dirac mass at 1/2, because the obvious transport here is the translation by a vector 1, and you're just doing half of it, move by 1. Okay. So once we have a notion of interpolation, we can, well, there's an associated notion of convexity. So if f is a functional on the space of probability measures, well, f is convex in the usual sense if f of mu t is less than 1 minus t f of mu 0 plus t f of mu 1. So that's usually convex, if you want. And we say that f is displacement convex if the same inequality holds, but with mu bar t, so with this notion of interpolation instead of the previous one. And okay, so what's the point of defining this? Well, one thing that's nice if you have convexity, if you have strict convexity, you have at most one minimizer. But that's true for any notion of convexity. So one application is, or one potential use is that if f is strictly displacement convex, so with the obvious notion, it's strictly displacement convex is this if this inequality is strict unless mu 0 equals mu 1, then it has at most one minimizer. Okay. Of course, if you're asking about minimizers among a certain class of, among a certain subset of this, you may need to check that your transportation preserves the subset on which you're working. So this was introduced by McCann in 1997, and with his, the application he is pursuing is this kind of application, finding uniqueness of minimizers for certain functionals, and he gives examples. So he says, well, there are kind of three big classes of functionals that you may be interested in. There's this one, this one, and so I think that's called, I mean, it's just some kind of potential functional. That's an interaction term, and that's internal energy. Anyway, doesn't really matter. So we can look at 3 families of functionals and ask, are they usually convex? Are they displacement convex? So I'm going to do a double entry. A, B, C.
Sorry, in
Sure.
functional, you're assuming you have some reference measure and you then look at the Radon-Nikodym derivative?
Yes, yeah, sorry, I should be more precise. Yes. So let's say it's always against
Like
Lebesgue
the
measure. Yeah, for me it's going to.
Yeah, it's the density of with respect to the
Yes,
measure,
yes,
and then
sorry.
you activate the
Yeah. Okay, so let's play the game. The first one, it's linear in mu in the usual sense. So it's convex, but not very interestingly convex, because it's never strictly convex. The second one is not convex in general. And even if W is. So even if your interaction potential W, so why is that the interaction? You think of X and Y as being 2 particles, and they interact through this potential W. So even if W is convex, you can find examples in which this is not convex. And C is complicated. Of course, it's but the relative entropy is convex. In fact, it's strictly convex. Yeah, so by the relative entropy is an example of case C. As case C, it's just log d mu d mu. Again, where d mu is the Radon-Nikodym derivative with respect to Lebesgue. Okay. Okay, so what about displacement convex? A is convex, is as convex as V. So if V is convex, that's convex, and if V is strictly convex, this is strictly convex. It's almost as convex as W. And for C, it's complicated, but the relative entropy is 9. So same. It's not the same complicated. The conditions are different, but the relative entropy is fine. Okay, so I'm going to do some very elementary computations to prove. I'm not going to prove all of this, but what's striking is that it's such a natural notion, and the proofs are also very easy. The only difficult proof here, or sort of difficult, is this: the fact that the relative entropy is convex for the displacement interpolation. And I'm not going to do that, but okay. So just to be convinced that it's very easy, let me prove A is displacement convex if V is convex. Well, you know, it's 2 lines, right? So let me compute this. By definition of d mu bar t, it's V of, if you want it, it's V of tt of x, which is V of 1 minus t x plus t t of x, d mu 0 of x. Okay, and then I'm using the convexity of V. Sorry, T. Right, so that's convexity of V. And then I just recognize that this is, well, this is the value for mu0, and v of t of x is just d mu0 is the same as v of x d mu1. So okay. 0 plus t d mu. Okay. Great. If you want to prove that B is displacement convex, if W is convex, exactly the same proof. Not, okay, very elementary, I agree. You could ask, okay, when is that strict? Or maybe you should, the question we could ask is, how do I get a strict convexity estimate at the level of the functional from a strict convexity assumption on V? Well, it's going to be here, right? That's the only place where I'm using the convexity of V. So can we make it quantitative? And you'll see why I'm spending time on such trivial matters. It's not. So well, there is always this if V is convex, you can always, so this is always and plus T V of y. And then there's a gain times the infimum of the second derivative of V on xy. So of course I can put this inequality here, and I will get something like so. If I assume that, let me write it here. So if we assume that, for example, that V is C convex in the sense that its second derivative is bounded below by C, then we get a quantitative estimate, which is minus T 1 minus T over 2, which is just given by integrating this with x being x and y being T of x. And so this should be here. If V is C convex, this inequality holds with a quantitative gain. And what we see appearing here is the cost, is the quadratic cost for the optimal transportation. And so that's a baby example of a functional inequality where you, in a sense, you have a quantitative convexity estimate or displacement convexity estimate that involves a certain distance between mu0 and mu1, which is here the minimal cost, the minimal quadratic cost that you have to pay to transport mu0 onto mu1. Okay?
So may I ask, so
sure.
all these conclusions are not dependent on whether T is optimal or not?
No. So no for A and B, and yes here. Here we need T to be optimal. So it's true that these computations are obviously not dependent of T being the optimal transportation, but if you want the relative entropy to be displacement convex, you're using the structure that the transport map is a gradient of a convex function. Okay. So I'm sorry if I was long, but and okay, last thing before I move on, I said here that it's almost as convex. What do I mean by that? If you do the same very, very simple computation for W. For W, you will apply convexity to W of t times tx minus ty plus 1 minus t of x minus y. So what you need to, so it's always going to be, if W is convex, then the functional is displacement convex. But if W is strictly convex, that's what I mean is that if W is a translation, there's no gain. And if t of x minus t of y is the same as x minus y, here you are not going to gain anything. Okay. So that's why I said almost. You have to pay attention a little bit. Okay, so let me move on. And let's talk a little bit about point processes. It's just a matter of giving a couple of definitions. So the first thing to introduce is what's a point configuration? Well, it's just, let's say on R. It's just a collection of points on R. I want it to be locally finite. So there's finitely many in any compact subset. And let me, this is the space of all configurations, and I will denote them by C. So you can see C as a sum of Dirac masses, and P are the points of C. So it's just a measure with typically infinite mass on R. And there's some, you can define a topology on it. Okay. So that's a point configuration. And a point process is just a random such thing. And a point process, it's just a random point configuration. Oh, for me, it's going to be a probability measure on point configurations. So it's not the random variable, it's the probability measure. Okay? It's not a very interesting difference. But. So let me give you an example. The Bernoulli point process in a box lambda with n points. So what do I mean by that is that I fix a box lambda and I throw n points uniformly in that box.
Why do you call it process? There is no time here.
That's just a... Well, you know, since you're on the real line, you could look at them as a time. There's no time involved at all. It's purely spatial. I call it process. And it's like the Poisson point process. There's no time, but it's a point process. Okay, so you just throw n points in lambda. And then there's the Poisson point process, which is really the limit of this when you take the big box. So I'm not going to define it, but it's sort of a lambda infinite version, or lambda equals R version of it. So for Poisson point process, first you, well, yeah, okay, that's easy. So the topology you want so that's just so that's just a different way to denote that, to be continuous for all phi okay. So it's a in particular, that's important. It's a local topology. In this topology, you can tell that two processes are closed in a big box, but you cannot distinguish them globally. Okay. And here's again something that looks innocent, but it's not so innocent. So the Bernoulli point process I told you is just you fix a box and you throw n points in it, and you look at the point configuration you get. That sounds very much like sampling the uniform measure on lambda n times. And in fact, so Bernoulli with n points in lambda, it's kind of, this is not a formal statement, but it's kind of isomorphic to the uniform measure on lambda n-fold. And I can describe the isomorphism if you want, as if you give me a configuration here, sorry. It's made of n Dirac masses. I will and actually okay. There will be a comment immediately. I will associate to it the following thing. I can take so I have n points in an interval. I can take the smallest one, and then the second smallest one, and then the biggest one. So what I get is not exactly the uniform measure. It's up to, if you want, it's the uniform measure on. Say.
Cycling. If you close it up to a circle.
Yes. Okay. But actually, I don't. Let's even. Okay. So that's not really the uniform measure. I'm sorry about that. But certainly, that gives you a random variable on lambda to the n. Okay. Or if you want it more precise, it's a probability measure. Right? Okay. The point I want to make is that this is at the level of point configurations where all the points are collected in one object. That's the point configuration. I can go back to something that's more familiar, which is a probability measure on a subset of Rn. Okay, that's all I want to say. And to do this in a concrete way, I can choose this enumeration. That's an explicit way of choosing an enumeration of the points. Okay, and I can do it because I'm on the line. In 2D, it would be less obvious how to enumerate the points. Okay, and the second point I want to make in the same vein is that, so here I'm on an interval and I have finitely many points. If P is a general point process, we can kind of see it as a measure on R to the Z. And if I take a configuration C, well, I can always enumerate. For example, one possible enumeration is to say that x0 is the first point after 0, or P0, if you want, P0, and P1, and P minus 1 is the first point to the left of 0, etc. And then send C to, well, the sequence Pk, K in Z. Okay. So the summary is that point processes are sort of like probability measures on R to the Z, point processes on the line. It's like R to the Z. And the optimal transportation setup that I defined earlier works for R to the little n for any n. And it's a natural question to ask, can you define a similar theory on R to the Z? So it's infinite dimensional, but countable. Right? So you could ask the so can we define optimal transportation on point processes which are somehow like R to the Z? And the answer is it's not clear. So I wanted to emphasize this because it's a natural question, in my opinion. It's kind of a natural extension of this well-established theory. But once you move to even just countably many coordinates, well, it's not obvious. So my collaborators, so Westman and Sturm and Westman and Matthias Ermer, they have some elements of answer, but there's no general theory for transporting point processes. And as a, let's just think of what we would need to get a good theory. Well, first, if you want to do optimal transportation, it's optimal with respect to some distance. And it's not obvious which distance is the interesting one. The point is that, of course, so it has to be sort of compatible with this, with this topology. But the topology is local. So if you want to separate points, you need to take distances in finite boxes and then in larger and larger boxes and combine them together. So it's not clear that there's a nice way to do this. Then once you have, okay, the notion of transport is obvious. It's just an application from the space of configurations to the space of configurations that pushes one measure onto the other. But is there any kind of nice structure of this map? The same way that there's a nice structure for the optimal transportation map in Rn? That's very much unclear. So nice structure, that's unclear. So we rely on an ad hoc, sort of an ad hoc construction here. But we hope that it can provide some insight for the more general question. Okay. Is there any questions so far?
It's very clear.
It's very clear? Thank you. Except for the terminology, right? Okay, perfect. So now I'm going to describe the question that we wanted to solve and that sort of led us to this discussion. I mean, they've been thinking about this problem, but bless you. So the question we were interested in comes from a different word, and I'm just going to give some notions. So in one word, the question was to prove uniqueness of minimizers for a certain functional that's the free energy of the log gas. I'm going to explain what I mean by that. So the log gas is a system of statistical physics, if you want, with n particles on the line. And they have a logarithmic repulsive interaction. What do I mean by that? And I mean that if you look at the positions of those particles, they have a certain energy which is given by a repulsive interaction that's proportional to the logarithm of the distance plus a confining term that I don't want to discuss. It's not really interesting for me here. And then so in statistical physics, you introduce a parameter beta, which is the inverse of the temperature, and you look at the system as being random. So you introduce a probability measure on all possible positions. And the probability of observing them is like exponential minus beta of the energy. So if you have a high energy, it's unlikely that you're going to be observed. That's called the Gibbs measure. What's my motivation to study those things? You have kind of two bits of motivation. One is you could treat that as a statistical physics problem, or it actually also comes from random metric theory. And in random metric theory, this is called a beta ensemble, and this is an object that's studied for its connection with random matrices. So if we accept that it's an interesting thing to study, what are the questions that we can ask? Well, there is a property, so this probability measure, that's a probability, so P and beta, is a probability measure on Rn. Okay. It minimizes the following variational problem. And it's the unique minimizer of the following functional. Well, really I should write it this way. So for any measure mu on Rn, you can compute the expectation of the energy with respect to mu. You can also compute the relative entropy of mu with respect to the Lebesgue measure n times. And if you can solve this variational problem explicitly, and that's what you get. That's also a simple computation. Okay. So where is the point process here? Well, it's coming. In statistical physics, and people like to take the thermodynamic limit, which is to send n to infinity. It's not only in statistical physics that people like to do that. So you could ask, okay, what happens as n goes to plus infinity? There is some sort of limit. I don't want to, in some sense, I don't want to be precise here. There is a limit object for this measure that's called sine beta, and it's a point process. So the idea is that for finite n, you have n points on the real line? Well, for when n goes to plus infinity, you have infinitely many points on the line, so you have a point configuration. P and beta was the measure for finite n, so the limit object will be some kind of measure on point configuration, so a point process. And the fact that there exists a limit is a pretty difficult result by Benedek Valco and Balin Virag. So they
Beta is 1/2 4 2. I mean 1 4
yeah.
2. Then you can.
Yes. Yes. Yeah. So it's general. The difficult part is that it exists for every beta. For certain values of beta, there is some miracle. There is some connection with random matrices that makes it somehow easier. But the derivation of the limit for every value of beta is a difficult result.
So is that for some particular confining term or for?
No, actually, it's universal in the confining term. So the proof is for a quadratic confinement, but it doesn't. In fact, it doesn't matter. Sorry. Okay. And what do I want to say?
You're just looking at the med. I mean, I'm familiar with the 1 4 2. Then one rescales to get local scaling. You get sine pi x over pi x. For a general beta, you're not looking at the local spacing. You're looking at sort of this global measure.
No, that's the local process here.
The right scale. Okay.
Yeah. Okay. And with Silvia Serfati, we introduced, in a sense, the equivalent of this variational problem, but in the infinite volume limit. So we introduced some functional that we denote by f beta of p, where p is a general point process. And it has the form.
Is your answer analytic in beta?
I'm going to come to that. So we have a variational problem. And here's what I'm going to explain a little bit about W and E in a minute. That's just a functional at the level of point processes. And so what is known is that P and beta minimizes a certain variational problem. It converges to sine beta, for which we have a variational problem. So it's a unique minimizer here. So we knew that sine beta minimizes f beta. And what we prove, so with Matthias Erbar and Martin Westman, is that it's the unique one. So maybe you can start to see where I'm going. I have a functional at the level of point processes, and I want to prove that it has a unique minimizer because I already know one minimizer. I know that sine beta is one minimizer of it. How do I prove that it's unique? I don't know. The bad piece of news is that W and E, which I haven't defined yet, are affine in P. So they are convex, but in a useless way. You'll never get strict convexity from an affine function. And so that's where Alice Guyonnet gave me very generously this idea. She said, well, there's a different way that you can prove uniqueness of minimizer, is if you prove that your functional is displacement convex. So the idea that Alice gave was show that f beta is displacement, is strictly displacement convex in some sense, but there is no theory of optimal transportation at the level of point processes. So you have to cook it up for yourself. Why is there a hope that such a thing would be true with the correct definition? Well, maybe I should say a word about W and E. So you see the finite n variational problem. You have beta times the expectation of the energy plus the entropy. And so W is also some kind of energy term, and E is also some kind of entropy term. I'm going to focus on the energy term because that's where the convexity comes from. So how do you define them? So definition of W and E. I will work in big boxes. So I will define WR of P as the following thing. It's the expectation under P of okay. So let's take a minute to discuss that. How do I compute WR of P? I take this big box, lambda R. I sample P, so I get a configuration C. So I get a bunch of points in lambda R in particular. I get a bunch of points on the whole real line. So in particular, I get a bunch of points here. And I compute their logarithmic interaction. That's very much the same as here. Right? It's the expectation under P of the logarithmic interaction of whatever you're observing. What about the entropy term? Well, you take your process, you look at it in this big box. It's a probability measure on configurations in this big box. And you compute the relative entropy in the usual sense of this with respect to the Poisson point process in the same box. So again, that's kind of very much like this term. But so Lebesgue n times is like Bernoulli process. And here I've switched to Poisson because I work in the infinite volume. You could put Bernoulli here, and that would give the same result. Anyway, and then you just define so that's a typical situation when you take an infinite volume limit, so a thermodynamic limit. Then your quantities are defined as finite volume quantities, and you need to divide this by the volume because they grow as the volume, and then you take the limit. You need to prove that this limit exists, and actually I'm cheating a little bit, but that's the main idea. So, okay, so here we have all the pieces in a sense. We have this functional, which is defined as an infinite volume limit of those functionals. And I would like to prove that it has a unique minimizer. For that, I would like to prove that it's some kind of displacement convex. Once again, let me go back to why is there hope? Well, the entropy is always convex. It's convex in the usual sense. It's convex in the displacement convex sense. So that should not cause any trouble. This term is of the interaction type. It's type B in my classification at the beginning. And the potential is minus log, which is convex on R plus. So here I'm working on the real line. So I have some functions are convex on the real line, or at least the positive half line. So since minus log is convex on R plus, there is some hope to prove convexity for f beta. Because if you remember, if W were convex, then the case B was also displacement convex. Okay, in the last minutes I have, I'm just going to sketch how the argument goes and just maybe insist on what is not so obvious. Okay, maybe before I do that, you might ask, why on earth do you want to prove that it's unique? This is a valid question, right? So this is a very difficult result, the existence of the limit. Okay, once you have the existence of the limit, and once you've derived some kind of variational principle, it's very easy to prove that sine beta has to minimize this. So you already know something about sine beta. Well, first of all, it's pleasant to have the answer to your questions. Maybe something that might be more convincing is that this derivation is remarkably difficult, and it doesn't use at all this sort of statistical physics point of view. It uses the random matrix theory point of view a lot. And as a consequence, the description of sine beta that they get is very on this random matrix side of the picture. If you prove that sine beta is the unique minimizer of this, well, in a sense, it gives you another definition of the limit process as the unique minimizer of a certain functional. So that can be satisfying. Okay, so I'm going to quickly sketch the argument and sorry.
Actually, could you leverage the variational theory to give a different proof of the result? Because often if you have this sufficiently strong convergence of the energies, you could actually just value by.
It's true.
That, right?
Not yet. It's not impossible, I would say, but it. Okay, so okay. Yeah. So the answer is it would be very nice. It's not a trivial consequence. Maybe let me put it this way. It's not impossible, but it's certainly not a trivial consequence.
Okay, so you were missing some of the kind of tools that you would have in a gamma convergence problem to actually use it.
Yes, if you want. Yeah.
To leverage.
Yes. Yeah.
But do you what are you missing? Just out of for a person who actually knows very well the gamma convergence side.
Well, the thing is that to prove that this minimizes this, we need to know that it exists. So maybe one point is like before sorry, let me take a minute. So there is some compactness at this level, okay, that tells you that a certain object has limit points, okay. But the compactness that comes, and it's not even for free, but that comes easily, is on an object that's not as precise as this. But if you know, the trick is that if you know the existence of the precise object, you also know something about the not precise object, and you can connect things that. I'm sorry, it's not very clear, but yeah. So what we know is that the non-precise object, and it's non-precise in the sense that it's average, must minimize f beta. Okay, and if this has a limit, then this has the same limit, and it has to minimize this. okay? But the fact that this has a limit is not clear, and it's so there is compactness at this level, but not at this level.
So you don't have compactness of the same.
Yes, exactly. So
spaces that you actually
exactly. So what I would know is that this has a limit, because there is compactness, and if there is a unique limit point, then it has a limit. But to get here is a little more challenging.
Okay.
If you want, it's really to go from a non-average object to an from an average object to a non-average object.
Can I
Sure.
ask which kind of convergence of the energies you have? So if you can-
So you mean what do I mean by this wiggly?
No. The energies, so
Oh, okay. So for this, there is gamma convergence. So
this there is,
yeah.
Okay.
To this W.
Okay.
So it's really the compactness which you lack. I mean, like the compactness that you would like to have is lacking.
Exactly. The compactness we would like to have is lacking, but it's not impossible to get it by statistical physics mean, but it really requires some work. Plus, to be honest, the connection between this and this is through this large deviation principle. So I'm lying a little bit when I say there's a variational problem. What I mean is that the probability that this object does not look like a minimizer of f beta is small. And so when you have to put all the pieces together, it's not clear that you can make it work. But yeah, it's a very tempting thing to study. Okay, so since I only have 5 minutes, I'm going to just emphasize the one point of the argument that's kind of none. So what's the sketch? You work in big boxes because everything is defined as a limit of big boxes. So work in big boxes. And what's great with working in big boxes is that in big boxes you have finitely many points. So you can use the optimal transportation in the classical sense. So you use optimal transport if you want in lambda r to the 2r, right? So lambda r is this interval. So typically you have 2r points because you have 1 point per unit length. That's just grant me this. So you're dealing with measures on this space. You can do classical theory. And then you use, displacement convexity. What is not obvious is that when you do the proof, just do the one-line proof of displacement convexity here. So just you use the fact that minus log is convex, blah, blah. You will get some gain, like the gain I had in my example at the beginning. Okay, you will get that a certain energy of the interpolate is less than 1/2 of the so here I should say, how does the proof work? It's a proof by contradiction. You want to prove that there is a unique minimizer? Well, assume there are two. Construct a better one. To do that, look at these two processes in a big box, transport one onto the other, and use displacement convexity. You should produce something that has a lower energy. That's true. And actually, there is a quantitative way to write that. But you need to ensure that the gain is proportional to the volume. Otherwise, you're going to lose it again. And that's where it's not completely obvious. So I could explain that, but I'm going to skip that. So, but once you've passed this difficulty, then so you've constructed a better process in a big box, and you can paste processes. You make IID copies in different boxes, and you construct a global thing, and you get a better candidate. So of course there are technical details, but yeah, maybe if I have 1 minute to conclude, maybe the question you had was so.
The reason I keep on asking it is Haldane.
I'm sorry?
Haldane has a conjecture for this for the correlations for any beta which is of the form P of the Q, and I think it's false. And if you tell me about the answer.
Okay, so there are, okay, so just quick.
He tried to extend the theorem for 1, 2, 4 to all rational.
Yes.
And he wrote down some wild
Yes.
conjecture.
Yeah.
False.
Okay. Okay. So maybe to like kind of summarize this, and so at the end of the day, you learn that sine beta is the unique minimizer of f beta. Okay. So what are the kind of questions you can ask? Well, you compute the free energy of this. That's a real number. And you can ask, is that regular in beta or smooth? So that's a typical question in statistical physics. If that fails to be C1, you say there is a first order phase transition. If that fails to be C2, there is a second order phase transition. In fact, it's analytic in beta because we have an explicit formula for this. But it's not super satisfying because that relies on an explicit computation that's only valid because you have the log, and it's kind of a miracle that you can compute it. So I would be happy to have a physical proof of at least C1 and C2 because the argument works only because minus log is convex. But you can replace minus log by something that's convex. Most of the argument would carry through. So that's one question. Sine beta is a family of point processes indexed by beta. Is there some kind of regularity of this object itself? And once again, there are some results by Valco and Virag, but if we had a sort of physical argument for that, I would be very happy. I didn't have the time to explain too much, but I told you at the beginning about these functional inequalities. So here I just mean, can you write your quantitative gain, convexity gain, in terms of the cost of the transport? And well, here we do it by hand, so it's not as nice as this, but we could hope that there is a nice distance on point processes for which this result actually follows from a functional inequality that would relate the energy and the distance and so on. And I'm going to stop. So there's a lot that's not known about sine beta, in particular the correlation functions. So it's known for certain values of beta, and there are some conjectures for every beta or a wide family of beta. But whether this characterization of sine beta as a minimizer of a certain functional could bring light to those questions is very open. Okay, so it's for going over time. Thank you.